Hi there. Welcome to the first lecture for Fox, where I'm going to try to give you a taste for discrete math and computing. Okay, now you should have watched already by now the warm-up, the welcome video, where basically I said that math is for anyone who's willing to put in the effort. So don't say math is not for you. And I'll just make one more point here, which is that math is a peculiar subject. It's just like any running or any sport, you have to train. So you have to do. You don't speed read math. It's not a spectator sport. Okay, so when you're reading through the books, please make sure that you do the pop quizzes. When I say, pause the video and do this, or pause the video and do this. Okay. Lastly, you should have already also watched the administrative stuff video, which goes through the web page. I'll discuss that very shortly today, but I won't be in any detail covering those two videos today. Okay, so let's begin. Okay, what's the plan for today? I'll tell you a little bit about the resources. I'll tell you about the storyline for this course, and then we'll talk a little bit about some background, and I'll present to you an interesting property of sets which you may not be aware of. The main goal for today is to show you how discrete math enters into the world of problem solving. So you have, and in a variety of applications. Okay, so you have an application and you can solve it with discrete math, and I'll show you how discrete math enters. And then we'll invoke some very famous people who have quoted and said that well, first of all, discrete math is fundamentally important to computer science. Point number one. And point number two, okay, that when it comes to getting good at math, effort is needed, patience is needed, perseverance is needed. Okay, I'll end with 3 challenge problems. I'll put my money where my mouth is. Okay, and I will offer $10 for one of the problems. That's an easy one. $100 for another problem, and you should be able to. Someone should be able to win the $100, and $1,000 for an even harder problem, and that is a very hard problem. Probably I've protected myself, but it's an interesting problem for you to think about. Okay, it gets at the heart of what is computing. Okay, so let's begin. So the resources, the web page, you can check out the web page and check out the administrative stuff video. Everything you need to succeed on the course is on the web page. Okay, the textbook is your friend, and if you bought a copy of the textbook, you should have a book that looks something like this. Okay. I highly recommend the book. Short chapters, one for each chapter, sets the schedule for the course. You can read the short chapter, you can understand the short chapter, work through the chapter. Don't speed read, don't be a spectator. Okay. We have the TAs and undergrad mentors, lots of energetic people ready to help you. The recitation section is going to be interesting for the online version of the course, so every homework has some recitation problems, and every week one of the TAs will record themselves working step by step through the problems. So look at the problems ahead of time, try to solve them, or even if you can't solve them, looking at them has a benefit, and then go and see how the TA solves it. Okay, ALAC hopefully will be able to provide some online resources for additional help. Keep in touch with them. Okay, I am always here. I welcome questions. I love it when you send me questions. Okay, I might not answer them immediately. That's not because I don't want to answer them. It's because I have to, I have a string of emails coming in and I answer them one by one. Okay, now prerequisites. They're not just there to provide a barrier to entry to this course so that we can weed out people. No. The prerequisites are there because you really should understand those basics before taking this course if you want to make the best out of this course. So programming up to data structure. So that's 1 year of programming. Calculus 1 is required and Calculus 2 is strongly recommended. So a full year of calculus. Okay, rules. No food. So you're watching the lecture or you're watching a recorded version of it. Don't be chomping on some, food and some crackers and this and that. If you are getting tired, no problem, pause. Okay, pause. Get something to eat, get a coffee, come back. But don't distract yourself while watching. No electronics. You don't need any electronics to do this course. You don't need it. Okay. Now, you might need a laptop to, write up the homeworks because the homeworks have to be typed. Exams have to be typed. And then to upload the homework to submit it, but otherwise no calculators, no calculating aids, nothing like that is necessary. No cheating, and that goes without saying, just don't do it. Okay? So let me tell you about the storyline. This is about discrete math. At the first half of this course, or maybe 2/3 of this course, is about discrete math. Okay, and in particular, to study discrete math, we need to introduce discrete objects, and then we will introduce how you reason about them, basically how you prove things about them. Okay, and one of the things we like to do with discrete objects is to count them, because imagine you have an algorithm, you have written a program that has to, search through all the possible ways of doing something. Well, how long will that algorithm take? Well, it'll take an amount of time that's essentially equal to the number of ways of doing that thing. So you need to be able to count how many ways can you do something. Okay, and counting 1, 2, 3, 4, 5, you're used to it, but when it comes to counting complex objects, like ways of doing something, we need some tools. Okay, and lastly, we need to sort of acknowledge that we're in the real world. In the real world, random things happen. So you send a packet down the internet, it doesn't always get to the destination. Some of them are dropped randomly. So we need to understand how randomness affects our reasoning about discrete objects and how it affects how maybe algorithms work and so on and so forth in the real world. And then it actually comes back full circle, and then we have realized today that certain algorithms actually inject randomness. So certain algorithms use randomness intricately in the actual algorithm itself. And the algorithm doesn't even go without the randomness. So it relies on randomness. Think about how we break ties at your wireless router, at your Wi-Fi router. So two people try to access, if they both try to access at the same time, they fail. So failure report. They try again, fail. Try again, fail. Try again, fail. So there's only one way to break this try again, fail situation, which is randomly. Okay, so randomness has become an intricate part of both understanding the real world and designing algorithms. So we need to understand randomness. Okay. That constitutes discrete math, or our treatment of discrete math in this course. And we could do a lot more, but we want to save some space and energy for the application of discrete math to the most famous discrete object, okay? So the digital computer. So we want to build a theory of computing. What can we compute? Okay, it's a deep question. And it turns out that we will be shocked by the answer. There are things that we cannot compute. Not only things we cannot compute, many things we cannot compute. So let's focus not on the things we cannot compute, but on what we can compute and what we can compute efficiently. Well, we'll touch on that, okay? But that will be the main topic of the follow-on algorithms course, okay? So, let me now discuss a little bit of background. Hopefully you all are aware of sets. Okay, you've had programming, you've had high school, so numbers, geometry, algebra, calculus, okay, and you've seen sets. Okay, so what's the minimum element in this set that I'm showing here? Okay, well, no brainer, 3. Okay, you just look at the set and you say it's 3. Okay, so let me pose a slightly harder question. What's the minimum element in this set, okay, of positive numbers? And, okay, I don't know, where this set ends, or how many numbers are in this set. All I know is that they're positive numbers, okay? And it could be an infinite set, so it's going on forever. Well, we don't know the minimum, okay? For example, we see 18 here, but is it the minimum? We don't know. But what do we know for sure? We know that the minimum is 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 18. Those are the only possibilities for the minimum, and it has to be one of them. And this is the case for any set of positive numbers. As long as it's non-empty, it must have a minimum. Okay? For example, if you look at the first element in any set of positive numbers, that gives you an upper bound on the minimum. So any set of positive numbers must have a minimum. That's a fundamental property of sets, and we're going to not focus on it now, but we will appeal to it heavily later. Okay, so today I want to give you a flavor for discrete math, so I'm going to move to the board so that, we're going to discuss some problems and how discrete math enters, and then, because I'm on the board, it means that, whatever I'm doing is at the speed at which I can write, so you can take notes. So take notes!